Welcome to the video lecture of subject electronic devices KC 301. In this video, I will be discussing about MOS capacitor, that is the topic of unit 5. We will see that what is MOS capacitor, what is its importance, and how the MOS capacitor is, what is the role of MOS capacitor in metal oxide semiconductor field effect transistor. MOS is an acronym for metal oxide semiconductor field effect transistor. So MOS capacitor separately does not have much application, but it is an important part of the MOS transistor. MOS capacitor. MOS is an acronym for metal oxide semiconductor that has a layer of metal, another layer of oxide, and third layer of semiconductor. A MOS capacitor is made up of semiconductor body or substrate and an insulator film such as SiO2 and a metal electrode called the gate. The oxide film can be as thin as 1.5 nanometer. 1 nanometer is equal to 10 angstrom or the size of the few oxide molecules. The figure is showing a MOS capacitor in which we can see there is a metal layer, then we have SiO2, and at the bottom there is a Si body. That silicon body is named as body part or the substrate of the MOS transistor. Before 1970, the gate was typically made of metal such as aluminium. Hence, the M in the MOSFET stands for that metal. After 1970s, heavily doped polysilicon have been used to make the gate terminal. So that material polysilicon that is being used due to its ability to withstand high temperature without reacting with SiO2. But the MOS name is still there even after replacing the metal layer with the polysilicon. Unless specified, we assume that the gate is made up of heavily doped, highly conductive polycrystalline silicon or polysilicon, we call it in short. After 2008, the trend to reinforce the metal gate and replaced SiO2 with more advanced dielectric for the most advanced transistor. The MOS capacitor is not a widely used device in itself, however, it is a part of the MOS transistor. So it is important for the analysis of MOS capacitor to have a understanding of the MOS capacitor. A MOS transistor is a MOS capacitor with two p-n junction that forming a capacitors. So this transistor of a structure, often a better structure for studying the MOS capacitor properties than the MOS capacitor itself. This figure is showing a MOS capacitor and having the N diffusion, that is an NMOS transistor in a MOS capacitor with PN junction at two ends. So here we can see there are two ends on which two diffusions are there, this N plus diffusion and N plus diffusion. So this part, that is gate SiO2, and P body, that is substrate, having two diffusion is the MOS transistor. So the complete working of MOS transistor that we will discuss later, and first we should know about that what is MOS capacitor and how its performance is being flat band condition and flat band voltage. The figure is showing the band diagram of the MOS capacitor. The structure, that is figure A, is the vertical placement of the MOS capacitor. It is the same figure that I have shown you in the previous slides, with the difference that here it is placed vertical. So on the left hand side we have N plus polysilicon gate. After that there is an SiO2 insulating layer, and we have a polysilicon body. Band diagram is shown in figure B, where in the middle we have the SiO2 layer, and the gap EC and EV is 9 electron volts. On the right hand side there is the band diagram for the body region, and on left hand side we have band diagram of gate region. So it is good strategy to first study the energy band diagram for a special bias condition that is called a flat band condition. For the figure that is shown here, we have Vg is equal to 0. So first, what is flat band condition? A flat band is a condition where the energy band Ec and Ev of the substrate is flat at Si-SiO2 interface. This condition is achieved by applying a negative voltage to the gate, thus raising the band diagram on the left hand side. When the band is flat in the body, the surface electric field in the substrate is 0. Therefore, the electric field in the oxide is also 0. That is, Ec, that is conduction band energy, and Ev, that is valence band energy of SiO2 are flat too. Ec and Ev of SiO2 are separated by 9 electron volts. The Eg of the SiO2, that E naught, that is the vacuum level, and vacuum level is the energy state of the electron outside the material. E naught, that is the vacuum level of SiO2, is above conduction band energy level Ec by 0.95 electron volts. The difference between E naught and Ec is called the electron affinity. Another material parameter, just as Eg is a material parameter, Si has an electron affinity equal to 4.05 electron volts. Eg is the material parameter. Si has an electron affinity is equal to 4.05 electron volts. E naught must be continuous at Si-SiO2 interface as shown in figure, otherwise the electric field would be infinite. Therefore, Ec of SiO2 is 3.1 electron volts higher than the conduction band energy level of Si. This 3.1 electron volt is the Si-SiO2 electron energy barrier. The whole energy barrier is 4.8 electron volt as shown in the figure. Because of these large energy barriers, electrons and holes normally cannot pass through the SiO2 gate dielectric. Ec, that is conduction band energy, in the polysilicon gate is also lower than the conduction band energy of SiO2 by 3.1 electron volts. The Si-SiO2 energy barrier, finally, Ef, that is Fermi energy level of the N plus polysilicon gate, may be assumed to coincide with conduction band energy level. That is just for the simplicity. In SiO2, the extra position of Ef has no significance. It does not require to place it at exact position. If we place Ef anywhere around the middle of the Si, N is equal to Nc exponential Ec minus Ef by kT would be meaninglessly small, such as 10 raised to the power minus 60 per centimeter cube. Therefore, the position of Ef in SiO2 is immaterial. The applied voltage at the flat band condition called VFB. The flat band voltage is the difference between Fermi level at the two terminals. VFB is equal to Xi C minus Xi S, where Xi Z is the gate work function and the Xi S is the semiconductor work function respectively in volts. The work function is the difference between E0 and EF. For an N plus polysilicon gate, the value of gate work function is 4.05 volts square, and for PSI body, the work function semiconductor work function is 4.05 volts plus EC minus EF by Q. Surface accumulation. How would the figure that we have seen change if a more negative Vg than VFB, that is flat band voltage, is applied? The band diagram of the gate side would be pushed upward. The result is we can see a upward bending in the bands. The figure that is shown is showing that upward bending of the band. This figure is not drawn to scale, that is 3.1 electron volts is not about the 3 times of the silicon band gap, just to save the page. Such non-to-scale drawing are the normal norms for this study. When Vg is not equal to VFB, phi S, that is surface voltage, and VOX, that is oxide voltage, will be non-zero in general. Q phi S is the band bending in substrate because the substrate is the voltage reference. Phi S is negative if EC bends upward towards the surface, as shown in figure, and positive if EC bends downwards. If this discussion of the sign of phi S sounds strange, then we can correlate it with the previous discussion of the band bend diagrams. VOX is the voltage across the oxide. Again, VOX is negative if SiO2 energy band tilts up towards the gate as it does in the figure, and positive if the tilts towards the gate. Because EV, that is valence band energy, is closer to EF, that is Fermi energy level at the surface, then in the bulk, the surface hole concentration PS is larger than the bulk hole concentration P0 is equal to Na. Specifically, PS is equal to Na e raised to the power minus q phi s by kT. Since phi s may be minus 100 or minus 200 millivolts, PS greater than equal, very greater than Na. That is to say, there are a large number of holes at or near the surface. They form an accumulation layer, and these holes are called the accumulation layer holes, and their charge, the accumulation charge, QAC. This condition is known as surface accumulation. If the substrate were N-type, the accumulation layer will hold electron. A relationship that we'll use again and again is Vg is equal to VFB plus phi S plus VOX. At flat band, Vg is equal to VFB, phi S is equal to VOX is equal to 0. So from the previous equation is satisfied. If Vg is not equal to VFB, The difference must be picked up by phi s and Vox. In the case of surface accumulation, phi s may be ignored in the first order model since it is quite small, and the previous equation we can write as Vox is equal to Vg minus Vfb. Using Gauss's law, Eox is equal to minus Qacc by epsilon Ox. We can write Vox is equal to Eox multiplied by Tox. That will be equal to minus Qacc divided by Cox, where Cox is the oxide capacitance per unit area, that is farad per centimeter square, and QACC is the accumulation charge coulomb per centimeter square. The above equation of Vox is usual capacitor relationship. V is equal to Q by C, or we can say Q is equal to C into V, except for negative sign. In V is equal to Q by C, the capacitor voltage and charge are both taken from the same electrode. In the MOS capacitor theory, the voltage is the gate voltage, but the charge is substrate charge, because interesting things happen in substrate. This unusual choice leads to the negative sign in the above equation. The equation of Vox is equal to Eox into Tox, and the Vox is equal to Vg minus Vf tells us that QACC is equal to minus Cox multiplied by Vg minus Vfb. Therefore, the MOS capacitor in accumulation behaves like a capacitor with Q is equal to CV or CVx that we have discussed earlier, but with a shift in V by Vfb. The shift is easily understandable because QACC is equal to 0 when Vg is equal to Vfb. In general, the previous equation of Vox should be read as Vox is equal to minus Q sub divided by Cox, where Q sub is all the charge that may be presented in the substrate, including QAC. Surface depletion. How would the figure change if more positive Vg than Vfb is applied? The band diagram on the gate side will be pulled downwards. As you can see in figure B, clearly there is now a depletion region at the surface because EF is far from EC and EV, and electron and hole densities are both small. This condition is called as surface depletion. The depletion region has a width W depletion. So the equation becomes Vox is equal to minus Q sub divided by Cox. Then we can write it as minus Q depletion upon Cox, and the charge we can write as QNA, width of the depletion, divided by Cox. Further simplifying it, we can write root Q Na 2 epsilon s phi s divided by Cox. So from here we will have phi s as Q multiplied by Na, depletion width square divided by 2 epsilon s. Q dep is the negative, having negative value because the acceptor ion after accepting the extra electron are negatively charged. So W depletion is equal to under root 2 epsilon s phi s divided by q n a. So combining the equations, we get Vg is equal to Vfb plus phi s plus Vox is equal to Vfb plus Q multiplied by Na W square depth divided by 2 epsilon s plus Qna W depletion divided by Cox. This equation can be solved to yield W depth as a function of Vg with depth determined Vox, and phi s become threshold condition and threshold voltage. Let us make Vg in the figure increasingly more positive. This bend the energy band down further. At some Vg, EF will be close enough to EC at the Si-SiO2 interface that the surface is no longer in depletion but at the threshold of the inversion. The term inversion means that the surface is inverted from p-type to n-type or electron-rich. Threshold is often defined as the condition when the surface electron concentration Ns is equal to the bulk doping concentration Na. That means the difference Ec minus Ef of the surface is equal to Ef minus Ev of the bulk, or A is equal to B. C is equal to D. Ei is a curve drawn at the mid-gap, which is halfway between Ec and Ev. Let the surface potential that is band bending at the threshold condition be phi S1. It is equal to C plus D divided by Q is equal to 2C by Q is equal to 2FB. Assuming NC is equal to NV, we can write Q phi B is equal to EG by 2 minus EF minus EV bulk, that is equal to KT ln NV upon Ni minus KT ln NV upon Na is equal to KT ln Na upon Ni. So phi s at the threshold condition is phi st is equal to 2 phi f is equal to 2 kt by q ln Na upon Ni. Then this kt value, that is kt Na upon Ni, where phi s at the threshold condition is defined as phi st is equal to 2 phi b, and that can be written as 2 kt by q ln Na upon Ni. The Vt at the threshold condition is called as threshold voltage Vt. So substituting, we get Vt is equal to Vfb plus 2 phi b plus under root Qna 2 epsilon s 2 phi b divided by Cox. The threshold voltage as a function of D oxide and body doping using this equation of Vt can be plotted. So the gate dielectric is assumed to be SiO2 with dielectric constant epsilon Ox is equal to 3.9. Strong inversion beyond threshold. Energy band diagram at the strong inversion when Vt is greater than Vt, we can analyze inversion layer which is filled with inversion electron. The inversion charge density is represented with Q InV Coulomb per centimeter square. Phi s does not increase much further beyond 2 phi b, since even at 0.1 volt phi b 0.1 volt further increases in phi s would induce a much larger surface electron density and therefore a large value of Vox that will soak up the Vg. If phi s does not increase, neither will be depletion region width. Approximately speaking, W depletion has reached its maximum value of Wd max is equal to under root 2 epsilon s 2 phi b divided by Qna. So here Vg can be written as VFB plus 2 phi b minus Q depletion minus Q inversion upon COX is equal to VFB plus 2 phi b plus under root QNA 2 epsilon s into phi b divided by COX minus Q inversion divided by COX, that will be equal to Vt minus Q inversion upon COX. So we can write Q inversion as minus COX Vg by Vg minus Vt. So this equation confirms that MOS capacitor in a strong inversion behaves like a capacitor except for the voltage offset of Vt. At Vt is equal to Vt, Q inversion is equal to 0. So we have assumed that electron will appear in the inversion layer whenever the closeness between EC and EF suggests their presence. However, there are few electrons in the p-type body and it can take minutes for thermal generations to generate the necessary electrons to form the inversion layer. So we can understand from the MOS transistor structure this problem. The inversion electrons are supplied by N plus junctions. The inversion layer may be visualized as a very thin N layer. Hence the term inversion of the surface conductivity type. The MOS transistor is more versatile structure for studying the MOS system than the MOS capacitor. So in this video, I have discussed about the basic MOS capacitor, how it works, its different modes, accumulation, depletion and inversion. Then we have seen weak inversion and strong inversion. We have also studied about the band bending due to the effect of depletion and accumulation of charges, and that is due to the effect of applied gate voltage.